Something that defies conventional physics. The results were so unexpected that even seasoned researchers are struggling to explain them. This wasn't just another routine experiment confirming what we already knew. Instead, it opened a Pandora's box of questions about the nature of reality itself. Quantum tunneling is a well-documented phenomenon in quantum mechanics, where particles like electrons pass through energy barriers they shouldn't be able to cross. It's strange, but it's something physicists have observed for decades. However, what CERN just discovered goes far beyond that. They weren't working with tiny particles. They were using particles 1,000 times larger than those typically involved in tunneling experiments. And yet these particles still pass through solid barriers, as if they weren't even there. This shouldn't happen. According to classical physics, larger particles don't behave this way. They don't just phase through walls. And yet the data doesn't lie. The Large Hadron Collider, LHC, recorded these events repeatedly with statistical significance so high that the chance of error is less than 1 in 3.5 million us. That's the gold standard in physics, the same threshold used when confirming the Higgs boson. So what does this mean? First, it challenges the boundary between the quantum world and the classical world. For years, we've assumed that quantum weirdness, superposition, entanglement, tunneling, only applies to the smallest particles. Electrons, photons, and atoms can behave in bizarre ways, but larger objects obey the predictable laws of Newtonian physics. But now that line is blurring. If particles much bigger than expected can tunnel, then maybe quantum effects aren't confined to the microscopic scale after all. This also raises questions about the Heisenberg uncertainty principle, one of the cornerstones of quantum mechanics. The principle states that we can't simultaneously know a particle's exact position and momentum. But if larger particles are tunneling, does this uncertainty still apply in the same way? Or are we seeing a breakdown in the rules we thought governed reality? Some physicists are even suggesting that quantum mechanics might need an update. A terrifying thought, given how much of modern technology relies on it. Then there's the energy problem. During the experiment, scientists noticed something even stranger. The particles seemed to gain energy as they tunneled. And this shouldn't be possible. The law of conservation of energy states that energy can't just appear out of nowhere. And yet the readings were clear. There was a brief but measurable spike in energy during the tunneling process. Where did it come from? Nobody knows yet. Some theories suggest it might be borrowed from quantum fluctuations in the vacuum of space, but that's speculative at best. What's even more mind-bending is that this effect didn't weaken as the particles got larger. In fact, in some cases, it became more pronounced. This goes against everything we thought we knew about quantum tunneling. Normally, the bigger the particle, the less likely it is to tunnel. But here, the rules seem to be flipped. So how did CERN manage to observe this when previous experiments at MIT and Caltech didn't? The answer lies in the precision of the LHC. The collider's detectors are so sensitive that they can pick up the faintest signals of quantum behavior, even in larger particles. Previous setups simply weren't advanced enough to catch these fleeting events. But why does this matter? Because if large-scale quantum tunneling is real, it could rewrite textbooks and lead to technologies we've only dreamed of. Imagine batteries that charge instantly because electrons tunnel through barriers without resistance, or quantum computers that don't need near absolute zero temperatures to function. Even more radical, what if we could harness this effect for new forms of propulsion, bending the rules of energy and motion in ways that seem like science fiction? And then there's the most tantalizing possibility of all, a link between quantum mechanics and gravity. For decades, physicists have struggled to reconcile these two pillars of modern science. Einstein's theory of general relativity explains the cosmos on a grand scale, while quantum mechanics governs the subatomic world. But the two don't play nicely together. This experiment, however, recorded tiny fluctuations in the local gravitational field during tunneling events. That's never been seen before. Could this be the first hint of quantum gravity? Oh, a theory that unifies all of physics. The implications are staggering. If quantum tunneling can influence gravity, even slightly, it might finally give us a way to test theories like string theory or the holographic principle, ideas that have remained purely mathematical until now. But before we get too ahead of ourselves, there's still skepticism. Extraordinary claims require extraordinary evidence. And while CERN's data is strong, it needs to be replicated. Other labs are already preparing their own experiments to verify these results. If they succeed, we could be looking at a paradigm shift in physics. So what's next? CERN is collaborating with other facilities, including LIGO, the Gravitational Wave Observatory, to dig deeper. They want to see if these gravitational anomalies are real or just experimental noise. Meanwhile, theorists are scrambling to adjust their models, trying to explain how large particles can tunnel without violating the laws of physics as we know them. One thing's for sure, the universe just got a lot weirder. And this might only be the beginning. If CERN's quantum tunneling breakthrough holds up under further testing, it won't just be a theoretical curiosity. It could reshape technology as we know it. From ultra-fast computing to unhackable networks, the practical applications of this discovery might arrive sooner than anyone expected. Let's break down how this could change everything. 1. The quantum computing revolution. No more freezing required. Right now, quantum computers are extremely fragile. They need to be isolated in near absolute zero vacuums because any tiny disturbance, heat, vibration, even stray photons, can destroy their quantum states, a problem called decoherence. But if larger particles can maintain quantum behavior, as CERN's experiment suggests, we might be able to build room-temperature quantum processors. Imagine a quantum computer that doesn't need a super-cooled lab, just a chip inside a regular desktop. That would slash costs, increase stability, and accelerate development by decades. Companies like Google and IBM are already racing to adapt these findings. If they succeed, we could see the first practical, scalable quantum machines within the next 10 years, not the distant future. 2. Batteries that charge in seconds. One of the biggest limitations in electronics is energy transfer speed. Electrons face resistance when moving through materials, which generates heat and slows charging. But if quantum tunneling can be controlled at macro scales, we could design zero-resistance circuits, where electrons bypass barriers entirely. This isn't just about faster phone charging. We're talking about instant charge electric cars, no more waiting at stations. Power grids with near lossless energy transfer, eliminating waste. Spacecraft with ultra-efficient propulsion, using quantum tunneling-based energy systems. Some researchers even speculate about quantum batteries, devices that store energy in quantum states, releasing it on demand without degradation. If realized, this could make fossil fuels obsolete. You're sure. 3. Unhackable quantum networks. Today's encryption relies on math problems that are hard for classical computers to solve, but quantum computers will eventually crack them, rendering current cybersecurity useless. The solution? Quantum encryption, where information is secured via quantum keys that collapse if intercepted. The problem? Quantum signals are delicate and degrade over long distances. But if large-scale tunneling allows quantum states to persist longer, we could build to global quantum networks, creating internet infrastructure that's physically impossible to hack. Governments and tech giants are pouring billions into this, and CERN's discovery might be the missing piece. 4. Medical breakthroughs, drug delivery through solid barriers. One of medicine's biggest challenges is the blood-brain barrier, a near impenetrable wall that protects the brain but also blocks life-saving drugs. Nanoparticles can sometimes slip through, but it's unreliable. Now imagine if we could engineer molecules to quantum tunnel way through this barrier. This could revolutionize treatments for Alzheimer's and Parkinson's, delivering drugs directly to affected brain regions. brain tumors, chemotherapy that bypasses healthy tissue, neurological disorders, precise, non-invasive therapies. Early-stage research is already exploring this, and CERN's findings could fast-track it. Dr. CERN 5. Stealth tech and quantum radar. If particles can tunnel through barriers, could we develop materials that let objects phase through walls? Not quite, but the military is already investigating quantum stealth coatings that absorb or tunnel radar waves, making aircraft truly invisible. Even more radical, quantum radar. Traditional radar bounces radio waves off objects, but stealth planes deflect or absorb them. A quantum radar system might detect objects by measuring disturbances in quantum fields, rendering EO current stealth tech obsolete. The dark matter connection. Here's where things get cosmic. 95% of the universe is dark matter and dark energy. Invisible, undetectable, and poorly understood. But what if dark matter isn't just out there? What if it's interacting with us via quantum tunneling, at scales we've never noticed? CERN's gravitational anomalies during tunneling suggest a possible link. If dark matter particles tunnel through ordinary matter without colliding, it would explain why we can't detect them directly. This could finally give us a way to probe the invisible universe. 7. Time crystals and perpetual motion. Sort of. In 2016, scientists created time crystals, structures that repeat in time, not space, defying normal thermodynamics. They require no energy input, almost like a perpetual motion machine, though they don't violate physics because they don't produce energy. Now combine that with CERN's energy spikes during tunneling. Could we stabilize these effects to create quantum energy loops? Not infinite energy, but for near-perpetual systems, for satellites, deep space probes, or even Earthbound power reserves. NASA and DARPA are watching closely. The risks. What could go wrong? With every breakthrough comes danger. If we can tunnel particles at macro scales, could we accidentally disrupt atomic structures? Unintended material decay? Create unstable energy fluctuations? Mini quantum leaks in power systems? Trigger unforeseen spacetime effects? Wildcard, we don't know yet. Theoretical physicists are running models to predict these risks, but one thing's certain: we're entering uncharted territory. What's next? CERN is already planning follow-up experiments, while labs worldwide scramble to replicate the results. If confirmed, we're looking at a technological domino effect. 1. 2025 to 2030. First room temperature quantum prototypes, 2030s. Commercial quantum batteries and ultra-secure networks, 3.0, 2040 and beyond. Potential breakthroughs in energy, medicine, and even space travel. But the biggest question remains: are we ready for what comes next? If CERN's quantum tunneling results are confirmed, they won't just change technology. They could rewrite the laws of physics itself. We might be standing at the edge of a scientific revolution as profound as Einstein's relativity or quantum mechanics. Let's explore how this discovery could shake the foundations of reality. 1. The quantum classical divide, a wall that doesn't exist. For over a century, physics has operated under a fundamental split. Quantum mechanics rules the subatomic world, particles acting as waves, entanglement, tunneling. On classical physics, governs the macro world, Newton's laws, predictable orbits, solid matter. But what if that divide is an illusion? CERN's experiment suggests that large particles can behave quantumly, meaning the cutoff between the two realms might not exist. This could force us to rethink everything, from how we model atoms to why we perceive reality as solid at all. Some theorists, like Roger Penrose, have long argued that quantum effects might play a role in human consciousness. If quantum behavior scales up, could our brains be exploiting tunneling or superposition? It sounds like sci-fi, but the math is suddenly worth revisiting. Novi Radkaranj 2.0 Einstein versus quantum mechanics, the final showdown. Einstein hated quantum randomness. His famous quote, "God does not play dice," reflected his belief in a deterministic universe. But quantum mechanics won, proving particles do behave randomly at tiny scales. Now CERN's findings might reopen that battle. If large particles tunnel deterministically without randomness, Einstein might have been onto something. Alternatively, if randomness still applies at macro scales, it implies the universe is far weirder than we thought. 3. The space-time anomaly. Is gravity a quantum effect? During the experiment, CERN detected tiny gravitational ripples during tunneling events. This is unprecedented. Gravity and quantum mechanics have always been separate, but what if they're linked through tunneling? Possible implications. Quantum gravity theory, a framework uniting general relativity with quantum mechanics. Wormholes. Some models suggest tunneling could mimic microscopic space-time shortcuts. Dark energy explained? If vacuum fluctuations tunnel, they might drive cosmic expansion. Deconari. 4. The multiverse connection. In quantum mechanics, particles exist in superpositions, multiple states at once, until observed. The many worlds interpretation says each possibility branches into a parallel universe. Most physicists treat this as philosophy, but what if tunneling proves it? If large particles tunnel, they might be interacting with alternate realities. Wild, yes, but if future experiments show particles borrowing energy from nowhere, it might hint at cross-universe leakage. 5. String theory's redemption? String theory, which proposes particles are tiny vibrating strings, has long been criticized for being untestable. But if tunneling reveals in extra dimensions, a key string theory prediction, that could change overnight. How? Tunneling particles might briefly vanish into higher dimensions. Energy spikes could hint at interactions with hidden spatial folds. If proven, this would be the biggest validation of string theory in history. Turnarn. 6. Time's arrow. Can tunneling reverse entropy? The second law of thermodynamics says entropy, disorder, always increases. Time only flows forward. But in quantum systems, time symmetry sometimes holds. If large particles tunnel backward, could they reverse entropy locally? This isn't time travel, but it might allow quantum systems to reset, a game changer for energy storage and computing. 7. The simulation hypothesis, a glitch in the matrix. If reality has hard-coded rules like classical physics, but we're finding quantum flexibility in the code, macro-scale tunneling, does that hint at a well-programmed universe? Some scientists, like Neil deGrasse Tyson, entertain this idea seriously. Eerie evidence. Tunneling's energy spikes resemble computational shortcuts. The unreasonable effectiveness of math in physics feels like optimized code. What's next? The experiments that could change everything. CERN isn't stopping. Upcoming tests include tunneling in living cells. Do biological systems exploit this? Gravity waves synchronized tunneling. Is space-time itself involved? AI-optimized quantum experiments. Letting machines find patterns we can't. Meanwhile, NASA and the ESA are studying whether CERN cosmic rays and exhibit similar tunneling, which could explain dark matter interactions. The biggest question, are we ready? History shows that when physics shifts, society follows. Quantum mechanics gave us transistors and nuclear power, but also the atomic bomb. This discovery could unlock clean energy, medical miracles, and interstellar travel, or unpredictable dangers. One thing's certain, the universe just got stranger, and we're only beginning to understand it.